majority of this the talks here in this workshop concerns about accelerating the computation. Okay, develop and use from first principle to force field, so we can accelerate molecular dynamics calculations. Okay, but my group, okay, I concerned with the other problem. Okay, the accuracy. Okay, how accurate, in particular, density functional theory. Then how do we use machine learning to improve? Okay, maybe ultimately solve this problem. Okay. So now we've been told there is a universal exact exchange correlation function now, right? But in practice, there are too many functionals. And for the beginner, certainly even for me, I don't know when my colleague came up with a problem, I don't know which functional to use. There's just too many. Okay, so this tells us, in fact, the system dependency, right? For different system, different problem, you use different functionals. Okay, so why is this? Okay. So now let's look at B3YP, the popular functional. Okay, well, okay, now I don't know if you can see my pointer, but anyway, so the exchange correlation energy is a hybrid, right? So actually there are many, well, in particular, the many terms, right? There are three parameters, A0, AX, and AC. Roughly they are like 0.8. Okay, so a mix of different functional. So this is being given. We use it, it's a universal. Okay, we use it, for any calculation. If you do BA3 or IP, that's what you use. Okay, but let's just imagine for the second formula expression here, we want to express this universal function now, okay, exact. If you want to borrow this B3YT form, what it would be? Okay, it's very simple. Now A0, X, AC, they are fixed number, right? But in fact, it should be a functional, right? If it is exact. So now A0 becomes A0 functional of electron density rho R, okay? AX as well, and AC, right? Now this has become immediately clear, okay? Because for different systems, the electron density function rho is different, right? Therefore, A0, AX, AC have to be different for different systems, right? So this is hence the system dependency. Okay, so this is why. So for any approximate function now, in principle, they are system dependent. That's where the system dependency is. Okay, all right. So now let's just again stick with this exact function now. Let's see. Let's write down the exchange correlation potential. Always like this. You take the derivative, okay, with different EX, EC, and a different exchange correlation functional we know, okay, different component. But in addition, we will have this term, right? We have to take the functional derivative with respect to A0. It's a functional, right? AX and AC. Okay, that's what it looks like. So the potential, if you look at the exchange potential, there will be extra terms on top of B3YP. Okay, that would be exact. All right, now let's assume, okay, because it's difficult. Well, in principle, I believe A0 rho we should be able to get it. Okay, but this is a topic maybe later we'll touch upon. Okay. But let's just for the moment, okay, this was almost 20 years ago, we said, okay, let's make approximation. Let's say A0 functional, AX functional, and AC functional does not depend on rho that much, okay? They're roughly 0.8, right? So therefore, we set this functional derivative with A0, AX, and AC20. Therefore, we get the same form for the exchange correlation functional as B3YP, except like the energies, this A0, AX, and AC has to be different for different systems. Okay, All right. So the question is, how do we determine, okay, this A0X for different system? And that was the paper we published almost 20 years ago, 2004. And we use machine learning. In fact, it's a neural net, okay? Basically, it's a very simple neural net. The input is spin, multiplicity, number of electron, dipole moment, kinetic energy, and the quadrupole moment of the molecules, okay? And output is A0, AX, AC, okay? For different molecule, we calculate input, okay? And, okay, well, so what is the result? Okay, well, let's look at the last column. Overall, this I think it's kcal per mole. We, in fact, okay, I think it's B2, okay, basis set. We calculate all two, okay, B2, about G2, okay, basis set. And overall, compared to B3YP conventional, all right, we improved somewhat. Okay, not significant, but there's improvement. Well, that's expected. Okay. All right. So, what to do next? Okay. Of course, we can improve the complexity. Okay, the input, and improve the complexity of the neural net. Okay. All right, that's what we could do. And also, we could put back in this functional dependence of A0, AX, and AC. In fact, one of my PhD students actually did it, okay? But it's difficult, okay, but we did it. But there was one problem that bothered me, okay, for really pursue it full time, okay? That's the transferability problem, okay? Because we need the data, right? For data for small system, you can, we need a very accurate data, or you use very high accurate method, okay? CCSD or maybe quantum Monte Carlo method, okay? But they're all limited to small system. For large molecule, we just don't have data, accurate data, okay? That's the problem, okay? But yet our input here, okay, needs electron density distribution of entire molecule. It's a global electron density, okay? So we don't have those data, okay? All right. So for training, for others, okay? So this is what I call the transferability problem, okay? What do we do, okay? This is it's a holographic electron density theorem, okay? It says very nicely for an entire molecule, okay? If we solve Schrödinger equations, okay, let's say, for example, the ground state, okay? Now, it turns out to be the ground state electron density function is a very nice mathematical function. It's a real analytical function. Okay, real analytical function means, okay, you can do, if you know electron density, real analytical function, a small region, okay, and you can do analytical continuation to know electron density far away. Okay. Well, you might want to say, oh, there might be singularity, like we are in the nuclear R. Well, that's okay because they're isolated points. You can always get around. Okay, so this is very nice. It says the electron density in a small region contains all the electron density information of the system. Right. Well, we know Helmholtz-Kohn, right? If you know electron density of the ground state electron density of the entire molecule or entire system, you know everything. So this is very nice, okay? So come back to what we are interested in, okay? Because we are stuck with rho as a global electron density, right? It's an analytical approach, and we don't have enough data for if that's the case. But then Now it says we don't need it. We just need electron density of a finite volume. That's it. Okay. All right. So here is our solution. Okay. Now let's look at this down. Okay. For instance, if we're interested in the well, let's say electron. Okay, let's go back to our problem, right? So for instance, exchange correlation potential, the exact, if you take a partial functional derivative, you end up with this, this is a function of functional, actually, in principle, functional of electron density of the entire system you are interested in, right? But then use our holographic electron density theorem, okay? All we need is, if we're interested in electron density in this red point, okay, exchange correlation functional potential, we all need is the electron density near, okay, because it encodes information further away. All right, then we can solve this transferability problem. Okay. All right, so this is what we did. Okay, a paper we published 2 years ago, finally. Okay. For instance, if we actually instead, for this particular talk, I will focus on the exchange correlation potential. In terms of density, the same thing. You use, holographic electron density theory, you can solve it, solve the transferability too. But for this talk, I focus on the electron density or exchange potential. Okay, so if we're interested in this calculate potential this way, what do we do? Exchange correlation potential. All we need is we take a little cube around this point here, okay, and then we take the electron density near as the descriptor, okay, as the input. Then we can predict what is the exchange correlation potential, okay, at this point through machine learning, okay, and this is the machine learning structure we use. Okay, we use this 3-dimensional convolution neural net. Okay, the input is, for this point is a cube. We divide the system into a different cube. The density we call the quasi-local electron density around the point of our interest, and then we also take the gradients, okay, around this. Okay, and then this is the structure. I don't have time to get into detail of this. So where the data coming from? We use CCSD, okay, double, single, double with partial triple. Okay, that's what we do for training. Okay. Now, once we trained, also we need the exchange correlation potential as a target, right? And that we use from Wei-Tao Yang's group, Wu Yang's method. Okay, and we calculate exchange correlation potential for training. Okay, so once this neural net is being trained, so what we do is, okay, we use a self-consistent method. Okay, so if for a new molecule, of course, you don't know the high precision, electron density, right? So what we do is we calculate, just say B3YP as an initial guess. We put it into this neural net. Okay, so it will come up with a potential. And this potential, for the first iteration, we'll put in a Kongxiang and solve for it. Okay, then we'll come up a new potential. And this new potential will be different. We put in, again, our neural net to predict a new exchange correlation function, or exchange correlation potential, and put in Kongxiang and solve it iteratively. Okay, that's what we do. Okay. So, okay, I will give you, this is give you some result. Okay, we start very simple, hydrogen molecule and a helium hydrogen plus. Okay, and we compare with B3YP. Okay, so we just look at density difference between our neural net method and with couple class as a reference, and also B3YP with couple class as a reference. Okay, so the orange line here is we plot the density around the axis. Okay, okay, around 2 proton. Okay, And this orange line is the density difference, okay, with CCSD. And this of course, B3YP is much bigger because this 2 peak correspond to where 2 proton are, okay. And this is helium hydro plus, okay. Again, we're better, okay. And we can calculate the force. Actually, once you have high precision density, you can use the Feynman formula and plus, basis set corrections. Okay, you can calculate the force. Actually, the force they're all quite close. Okay, or in a larger scale. But if you zoom in at near the equilibrium for helium hydro plus, actually our method is better than B3YP. Okay, even in terms of equilibrium position, it's better. Okay. Now the question is, if you, in fact, we train, for instance, for let me see, helium hydro plus, okay. We train only up to internuclear distance. I think it's around 0.9 Armstrong. Okay, so what we did is we stretch. Okay, we stretch the internuclear distance. We look at the force. Actually, it still works. Okay, I did not really expect, but it's nice to see. Okay, so we trained up to the total line, dash line here. Okay, all right. So anyway, and also we look at this one, the internuclear distance beyond our training range set. Okay, actually is still better, okay, than B3YP. So we have 2 nuclear, 2 electrons. So let's say, can we do new system, right? Just use the 2 nuclear. We use 4 nuclear. Okay, this is helium, hydrogen, and helium. Okay, it's lined up. Okay, so we have 4 nuclear, 4 electrons, but the training set only is 2 nuclear, 2 electrons. Okay, and this C is the result. Okay, for different internuclear distance. Again, compared to B3YP, or not compared to with contrast CCSD. Okay, result as a reference. Okay, on was much better than B3YP. Okay, another problem is venomous interactions. Okay, in fact, we use helium dimer. Okay, and the upper panel, we compare B3YP with our neural net. Okay, we use counter plot. Okay, in the going through the nuclear this plot. Okay, and again, and the color code the difference to the CCSD result. Okay, again, it's much better in terms of difference. Okay, much better B3YP, as well as the force and the potential. Okay, all right. So as I run out of time, I will speed up. Okay, and right now we're looking at some organic. This is formaldehyde again. This is now we have much more, 4 protons and 4 nuclear and more electrons. Again, compared to compared to B3YP, better. Again, this counter plot. Okay, all right. So in the rest of time, I want to switch gear a little bit. Okay, now I assert, okay, all the most, okay, except quantum Monte Carlo, okay, all the first principle calculation, I've been calculating the error, okay, compared to exact result are systematic. Okay, they are systematic error. By definition, systematic error can be corrected, calibrated, right? So what we can do, we use machine learning to do this. Okay, all right. Now, this is a work we did again 20 years ago with Hu Lihong and Wang Xiujun. They are now both professors in mainland China. Okay. We look at a very simple organic molecule, 180 small, medium-sized organic molecule. We calculate heat of formation. Okay, so the vertical line is the experiment. Okay, the horizontal line is with B3YP calculation. Well, their training is good. qualitatively correct, but quantitatively not. Actually, the error is pretty large. Okay, IMS error is about 20 kcal per mole. Okay, then what we did is, as I said, they can be corrected, right? So we're again use a very simple neural net, and after this, okay, it's reduced almost order of magnitude. Okay, training, of course, testing as well. Okay, so let me just show you what kind of molecule looks like. These are the molecules, and the underlying one actually is the one in the testing set. You know, the experiment, say, calculated result is about -38 kcal per mole, and DFT calculation actually is 7. Even the sign is not correct, but we can use calibration. This very simple method, okay, to do this. Later on, we can actually make use of machine learning. Okay, actually we can tell, okay, the uncertainty of our predictions. Now, when we do calculation, we don't tell how accurate this result is. Now we can do it. Okay, we use machine learning. Okay, so here the arrow bar given is the calculation, the uncertainty, and here you see there are a lot of short line, blue lines, represent each data in the training set. Okay, each molecules. Okay, and when the density, okay, this is represent the density is, this means density is very high, and then the uncertainty of prediction is very small. But when the error bar, I mean, there's sparse, and the error bar is large. Okay, all right. So anyway, okay, just I want to say Professor Xu also did work, very nice work along the line, but I don't have time to get into detail. Okay. Finally, I want to finish my talk with this question. Okay, can we use deep learning to predict the experimental measurement, the value of experimental measurement for our molecular properties? Can we do this? Why? We don't have enough data. Okay, because experimental data is hard to get. Okay. Can we do this? Okay. So, in fact, that's easy. Okay. Now, if you think about it, trivial. So, what we do is we first, like most people, use deep learning to reproduce DFT result. Okay. Then what we do is use what developed, started 20 years ago. Okay, whereas we don't have a lot of data. Maybe only have 100 or a couple hundred data. Okay, then we use the output of the deep learning, which is try to reproduce DFT result, right, as this one, and then correct it with a simple neural net. Okay, so I will not get into detail. I'm just to say that can be done. Okay, and before closing, I want to say something. Okay, now, in fact, what we try to solve this exchange correlation problem. Okay, we want to come up with a universal answer. Okay, that's still fundamental research, right? But practically, I think it's my belief. Okay, the second approach can be very useful, because often we see DFT is qualitatively correct. Okay, quantitatively we have problem, maybe semi-quantitatively correct. But then this is very useful, okay, because the train is okay. So then what you need, you don't need this really fancy methodology, okay? You just use limited experiment, you can correct. Of course, this is for specific problem, specific system. Okay, but working with experimentalist, this approach should be very useful. Okay. Finally, students did all this. Start with Zheng Xiao, Hu Lihong, why there was a PhD student in my group. Okay, and there's some recent PhD student in my group as well. Okay. Thank you very much.